Today we will start with part 4 of the material in this course, and this is about the operational amplifier. The operational amplifier, start first with the symbol, the triangle with the minus and the plus, and two power supplies in general. It has two inputs, one output. One input is connected to a minus sign, the other input connected to a plus sign. This is a very important building block in analog electronics. The reason why it's called operational amplifier is because it can be used, this circuit can be used in all kinds of operations, to implement all kinds of operations, of course, amplification, which is like multiplying by a gain, by a constant, addition, subtraction, division, calculating an exponential, integrating, differentiating, solving differential equations. All of those things can be done using op-amps or circuits that have op-amps in them. So they're very important and very useful, and we would like to learn more about them. First, about their characteristics as a building block, and then as circuits, so what is inside them. If we want to build an op-amp, how can we build one? Let's start with the ideal case first. For an ideal op-amp, we said that we have these two inputs, input at node 1, another input at node 2, and the output is at node 3, and two supplies, a positive supply and a negative supply. In general, I will have two supplies. In some cases, I may have just one positive supply. The input that's connected to the minus is called the inverting input. The input connected to the plus is called the non-inverting input. For the ideal case, there is no input current, neither at the inverting nor at the non-inverting input. So the input current is 0 at 1 and at 2. And this means that there is an infinite input resistance. The output is some A times the difference between the potential at 2, the plus, and the potential at 1, the minus. So V at the output, V3, is A times V2 minus V1. And ideally, this is always A times V2 minus V1, irrespective of what's connected to it. In other words, the output resistance is 0. So infinite input resistance, 0 output resistance, no matter what is connected at the output. V3 would be A times V2 minus V1. Not just that, but also in an ideal op-amp, A is infinite. So when we say V3 is A times V2 minus V1, also this A that we call the open loop gain in an ideal op-amp is infinite. So infinite input impedance, 0 output impedance, and infinite open loop gain, which is surprising, because if A is infinite, what happens to the output? Infinity times something. If V2 minus V1 is some volt or millivolt quantity, multiply by infinity, you get an infinite output, according to this equation. But that's not actually the case. Let's see why. The reason is the output voltage saturation. So the op-amp output voltage actually saturates within 1 volt of the power supplies. So we have two power supplies, VCC and minus VEE. The output voltage will actually saturate within a volt of the supplies. For some op-amps called rail-to-rail, the output voltage can reach to within a few millivolts of the supply. So if the supply is 10, or the two supplies are 10 and minus 10, the output voltage can reach maybe 9, 9.5, close to 10 in the positive direction, and minus 9, minus 9.5, minus 9.9 in the negative direction, but then it saturates. It cannot increase beyond 10 or drop below minus 10. And we've seen this, and it causes clipping in the waveforms and distortion. But this also happens at the output of an op-amp. We get output voltage saturation. So what does this mean? Why is this related to A being infinite? This is related because this equation, V3 is A times V2 minus V1, only applies if the voltage is not saturated. If the output voltage does not reach saturation, this equation applies. V3 is A times V2 minus V1. So this equation applies only when the output is not saturated. And if the output is not saturated, it's between the supply levels, then it's finite. And if A is infinite, so this is finite, this is ideally infinite, what does this imply? This implies that V2 minus V1 is some finite number, which is the output voltage, divided by infinity. So V3 over A, and this will go to 0, which means that V2 is equal to V1. So V2 and V1 become equal when the output is not saturated. So if I want to avoid saturation and distortion and clipping, and I have an ideal op-amp, the two inputs at the minus and at the plus will have to be equal, because A is infinite and the output is not saturated, and this equation would apply. And this is what we call the virtual short between the two inputs. So when I have these two inputs at minus and plus, as long as the output voltage is not saturated, V1 has to be equal to V2. Because the equation applies, V3 is A times V2 minus V1, and V3 is finite, and A is infinite. So V1 should be equal to V2. This equation would not apply if the output is saturated. So don't try to apply it. Don't try to convince yourself or others that V2 is equal to V1 if the output is saturated. The equation does not hold. In other words, you can force V1 and V2 to be not equal. So you can apply 1 volt at input 1 and 3 volt at input 2. And you will get an output, but it will not be A times V2 minus V1, because you will saturate the op-amp, and therefore this equation would not apply. If the op-amp is not saturated, the output is not saturated, this equation would apply. And if this equation applies, the two inputs must be equal. So this is the virtual short between the two inputs when the output is not saturated, and the gain, the open loop gain, A of the op-amp, is assumed infinite. So this is the ideal case. Let's try to apply it in some simple configurations. Let's build an inverting amplifier configuration. I don't want an amplifier with infinite gain. Maybe I want just an amplifier with a gain of minus 15, minus 20. How can I build one out of op amps? Here's a very simple and very popular circuit to build an inverting amplifier. I have an input. The input signal is coming from VI. Two resistors, R1 and R2, the op amp, and I take the output right from the output of the operation amplifier. So what is VO over VI? What will be the gain in this case? I'm assuming that this is an ideal op amp. So the input currents will be 0. The output is not saturated because I'm building an amplifier. I want the signal to be clean. I have therefore infinite gain, infinite A. And this means that the voltage at nodes 1 and 2 will be equal. So since 2 is connected to ground, and since there is no potential difference between 1 and 2, the voltage at 1 will also be 0. Because V1 minus V2 is 0, and V2 is 0. If the voltage at 1 is 0, I can find the current in R1. It will be VI minus 0 over R1. But there is no current flowing into the op-amp input because the input resistance is infinite. So this current flowing in R1 will continue and it will flow in R2. And then I can apply Ohm's law to R2 and say that V1 minus V3 is R2 times this current. And that's how I can get to V3, which is the output. So these are the steps. Step number 1, I have a virtual short between the two inputs because the amplifier is operating linearly, no saturation, and A goes to infinity. So this results in a virtual short between the two inputs. So this means that here at this node, I have 0. So what's the current in R1? VI minus 0 over R1. So this is the current in R1. But there's no input current into the op amp. This means that the current in R2 is equal to the current in R1. So I2 is equal to VI over R1. And then we apply Ohm's law to R2, and we get VO equals minus R2 over R1 VI. A very simple and very well-known relationship for such a circuit. You get a gain, which is minus R2 over R1. So inverting, negative gain. And the gain is the ratio of the two resistors. That's a very useful, simple, nice circuit. If you want a certain gain, you get an op amp, get two resistors in the right ratio, and you get a nice amplifier with the gain that you need. The input resistance for the whole circuit here, VI over II, would be R1. And if you calculate the output resistance, because this is assumed ideal, the output resistance for the whole thing also would be 0. When the output resistance is 0, it means that the output voltage is not affected by whatever load you connect at the output. So this is the inverting amplifier configuration. Input and output are out of phase. There is a minus sign in the gain equation. And there is a trade-off between large input resistance and large gain. Because the input resistance is R1, if you want a large input resistance, you have to make R1 large. But if you make R1 large, the gain would suffer. Or you'd have to make R2 also large to keep the same ratio to get the same gain. Now let's consider the case when A, the open loop gain, is not infinite. So A in this case, I don't want to assume that it's infinite. What happens if I assume that A is not infinite? Well, the equation V3 equals A into V2 minus V1 would apply, but A would not be infinite here. So in this circuit, with V2 being shorted, being exactly 0, because the node 2 is shorted to ground, this will go to 0. This is not infinite. So not infinity. What does this mean? It means that V1 would be minus VO over A, since V2 is 0. So now we see that if A is not infinite, there is something, some signal would appear at node 1. And as A goes to infinity, this signal goes to 0. All right, so now I have to modify the current equation. The current in R1 would be VI minus V1. This current would be the voltage here minus V1, which is no longer 0 over R1. So that's II. And also this, I'll continue to assume that there is an infinite input resistance. So this current will continue in R2. And this is the application of Ohm's law for R2. So let's rearrange and see what is VO over VI in this case. AV, the gain, would be minus R2 over R1, what we got previously, divided by 1 plus R2 over R1 over A. So this is consistent with the previous result, because if A goes to infinity, this term would go to 0, and AV would be minus R2 over R1. So consistent with the previous result. A is usually very large, and the error term, the error in this expression is usually very small. So still, if I want the voltage gain with finite A, this is the expression that I can use. We call this the error term, which goes to 0 as A goes to infinity. Here's another application of this circuit, the inverting amplifier. The summing amplifier is actually an application of the inverting amplifier with superposition. So if you consider just R1 with RF and forget about R2, V2 to Rn, Vn, the circuit will be an inverting amplifier for V1. If you forget about V1 and R1 and just consider V2 and R2, the circuit will be an inverting amplifier for V2. And so on and so forth until Vn, the circuit is an inverting amplifier for Vn. And now I can apply superposition and say that if I only have V1, the output will be minus the expression that we derived, Rf over R1 times V1. If I only had V2, then the output will be minus Rf over R2 V2, and so on. And by superposition, if I have V1 and V2 and V3 and Vn, since the circuit is linear, the equations are all linear, I can sum all of these minus Rf over Ri times Vi, and I get Vo equals minus Rf over R1 V1 plus Rf over R2 V2 plus Rf over Rn Vn. So this means that the output here is the sum or the weighted sum of the inputs, but it's inverted. So I can have VO, for example, minus 2V1 plus 4V2 plus 6.5 V3. That's very easy to implement. I need an op amp and 4 resistors, R1, R2, R3, and RF. And I select the resistors in such a way that RF over R1 is 2, RF over R2 is 4, and RF over R3 is 6.5. And I get a nice circuit that will give me the sum. And it's not a simple sum, it's weighted. I can make it just a sum. I can make it V1 plus V2 plus V3 if I make R1 equal to R2 equal to R3. But this is more general. I can come up with a weighted sum expression for the output. And this is a minus sign here, but I can easily get rid of it. I can use maybe another op amp to just invert, and then I get rid of the minus sign. Another popular amplifier configuration that you may have seen is the non-inverting op amp amplifier configuration. Here, the input is directly applied to the non-inverting input here, and the output is, of course, at the op amp output. And I also have 2 resistors, R1 and R2. Their common terminal is connected to the inverting input of the op amp. R1 is between the inverting input and ground. R2 is between the inverting input and the output. So again, we can analyze this using the first the ideal situation. So here I have the voltage at this node is equal to VI, and then I have a virtual short circuit between the 2 inputs if I assume that the gain, the open loop gain of the op amp is infinite. So this means that the voltage here is also VI. And now I can find this current. It will be VI over R1. And this is equal to this current, which is VO minus VI over R2. So VO minus VI over R2 is equal to VI over R1. And that gives me another famous expression for gain in this case. The gain for the non-inverting op amp amplifier configuration, 1 plus R2 over R1. So at least 1, and it's positive. The input resistance here, there's no input current because the input current has to flow into the op amp. So II is 0, and the input resistance is infinite. The output resistance is 0 because I'm assuming an ideal op amp. If A is finite, what do we get? We get the same expression and the same error term. So 1 plus R2 over R1. This is the gain when A is infinite, divided by 1 plus the error term of the previous amplifier configuration. 1 plus R2 over R1 over A. And of course, as A goes to infinity, the gain for finite A would tend to 1 plus R2 over R1. So in this case, the input and the output signals are in phase, and the input resistance is infinite. In phase, the gain is positive. One more very simple application is the voltage follower, which is just like a buffer. It takes the input voltage and produces an output which is exactly equal to the input. And we can do this by taking the output and connecting it to the inverting input and applying the input to the plus. So the virtual short should make this equal to VI, but this is connected to VO. So VO is therefore equal to VI. That's called a voltage follower. And the reason why we would need a circuit like this is when I have a voltage source and I don't want to load it, I don't want to take any current from it, I can connect it to a voltage follower. The op-amp would not take any current from the source and would produce a voltage here that is exactly equal to the voltage here. And now I can connect anything, any load here that can take any current, and the output voltage would still be equal to VI. So while that was not possible, connecting the load directly here was not possible, now it becomes possible with the voltage follower. And this is the model, just an ideal voltage source controlled by the input and exactly equal to the input. So infinite input resistance, zero output resistance, and gain exactly equal to 1. Okay, now let's try to design a difference amplifier. I want to come up with a circuit that gives me the difference of two signals and that would amplify it. You may think that the op-amp already does that. It amplifies the difference between two signals. But this is not what I have in mind. This is not what I need. I don't want a circuit that will give me some infinite gain times the difference V2 minus V1. I want maybe a gain of 20. So I want an output signal which is 20 times V2 minus V1, or 10 times, or something like that. The op-amp has, yes, it does amplify the difference, but it amplifies it with a gain of infinity. And I don't need infinite gain. I just want some finite gain. 10, 20, 30, 50, something like that. So how can I build an amplifier using an op-amp maybe that will give me some gain that I have in mind? I have specifications. I need to build a difference amplifier. It should amplify the difference, only the difference. And it should give me a certain gain. So I have two input signals, and I want to build an amplifier that amplifies the difference of these two input signals. So I call them VI1 and VI2. And I want the output to be some gain times VI1 minus VI2, or VI2 minus VI1. Since I'm interested in the difference, I will define this difference. I will call it VID. So VI2 minus VI1, this is the quantity that I want to amplify. I'll call it VID. And if I want to make a complete change of variables, I will also define the average and call it VICM. The average is half VI1 plus VI2. Now with the average and the difference, I can go back. I can tell what is VI1 and what is VI2. So this is like a change of variable. Instead of dealing with two input signals independently, since I'm interested in the difference, I want to focus on VID. But VID alone does not allow me to know what was VI1 and what was VI2. So I introduce also the average. The average is there so that I can go back to VI1 and VI2 if I need to. But it's not. I don't want it to appear in the output. So the difference and the average. Another term we use for average is common mode. That's why it's called VICM, common mode, the average between the two inputs. So the difference is VID, the average or common mode is VICM. The difference is just the difference, VI2 minus VI1, and the average is half VI2 plus VI1. So I can easily go back to VI1 and VI2 if I know the average and the difference. VI1 would be the average minus 1/2 the difference, and VI2 would be the average plus 1/2 the difference. So this is what we call change of variables, and we're doing it for convenience because I want to emphasize VID. I want to see VID. This is what I want to amplify. All right, and so we can go in the two directions. If I know VI1 and VI2, I can find VID and VICM. If I know VID and VICM, I can go back to VI1 and VI2, as you see in these equations. So two input signals. In general, if I have a linear circuit, if I have two input signals, the linear circuit should, the output should be some combination of VI1, A1 VI1 plus A2 VI2. So superposition should apply. That's in general. Linear circuit, two inputs, the output would be some A1 times VI1 plus some A2 times VI2. I'm not saying that A1 and A2 are gains or larger than one, whatever they are. Any two numbers, if I have a linear circuit, two inputs, one output, this would apply. Output would be some A1 times the first input plus some A2 times the second input. But VI1 is this expression, and VI2 is this expression. So A1 times VICM minus VID over 2, that's A1 VI1, plus A2 times VICM plus VID over 2, that's A2 times VI2. Okay, so let's collect the terms that have VICM. I get A1 plus A2 times VICM plus A2 minus A1 times VID. So I'll call this quantity A1 plus A2, I'll call it ACM, and I'll call this quantity A2 minus A1 over 2 that multiplies VID, I'll call it AD. So the output, therefore, so this is the output. The output can also be expressed as some quantity ACM times the average plus another quantity AD times the difference. So ACM VICM plus AD times VID. That's another way to write the output for this linear circuit. And that's a very useful expression because it shows that the output is some differential gain. This is the gain that amplifies, that multiplies the difference times the difference plus some common mode gain that multiplies the average over the common mode. And if I want to directly define AD, it is VO over VID when VICM is 0, when the average is 0. And ACM is VO over VICM when the difference is 0. If the difference is 0, it means that the two inputs are equal. If the average is 0, it means that the inputs are opposite. VI1 is minus VI2. So that's the definition of AD and ACM. And they're, of course, equal to ACM is A1 plus A2, and AD is A2 minus A1 over 2. So this is a simple math rearranging of the term, doing a simple change of variable so that we emphasize this is what we're after. I want to see something like this. Why? Because I am after this. I'm building a circuit that will give me VO equals AD times VID. I want to get rid of the ACM, VICM. This is a term that I want to make 0. I don't want to see this. I want the output to be just again AD times VID. So now I can see them in front of me. When it was A1 VI1 plus A2 VI2, it wasn't clear. What should I do? Should I make A1 equal to what and A2 equal to what? Now I can see it. VO is AD VID, that's the good part, plus ACM VICM, that's the bad part. And I want to get rid of the bad part. So if I have in general this output, I want to only keep AD VID. Let's define a term before we continue with the circuit design. This is a quantity that we see in op amps and in difference amplifiers. The common mode rejection ratio is 20 log base 10 of absolute value of AD over ACM. If I have a difference amplifier and it only amplifies the difference, ACM should be 0. And the CMRR would go to infinity. The ideal CMRR for an ideal differential amplifier would be infinite. But in real amplifiers, it's not infinite. And we look at the number, this is in dB, the higher the CMRR, the better the differential amplifier. So 100 dB would be a nice CMRR. Ideally, it's infinite, but we will not get an ideal situation with real circuit components. So let's go back to our circuit design and let's try something like this. An op amp with 4 resistors, and of course I have these 2 inputs. I want to amplify their difference, produce it here at the output, and let's see if this circuit allows me to do that. Let's apply superposition. Again, the circuit is linear and superposition is very helpful. So we assume that one input is 0. We find the output as a function of the non-zero input, and then we reverse the roles and find the output again, and then add the 2. So let's first set VI2 to 0. So this is VI2 here, and I will set it to 0. If I set VI2 to 0, it means that I connect this to ground. When I set VI1 to 0, as if I connect this to ground. So setting VI2 to 0 makes R3 and R4 connected in parallel, and VI1 is connected to R1. This is a very simple inverting op amp configuration. VO is minus R2 over R1 VI1. The presence of R3 and R4 would not affect the result because there is no current in them. The current here is 0, and therefore there's no current in R3 or R4. What about the other input? When I set VI1 to 0 and I have VI2, this looks like a non-inverting, let's call this V plus VP. This is like a non-inverting amplifier configuration, and VO2 would be VP times 1 plus R2 over R1. But VP is not equal to VI2. I have a voltage divider that gives me VP from VI2. So VO is 1 plus R2 over R1 VP. And VP is the voltage divider here, R4 over R3 plus R4 times VI2. So that's VO when I have VI2 and no VI1. With superposition now, I can find the voltage when I have VI2 and VI1, and that will be minus R2 over R1 VI1 plus the longer expression for VI2, 1 plus R2 over R1 into R4 over R3 plus R4 VI2. Okay, so this is what I get, and now I will need to do some maybe mathematical expansion here. So I will take this and replace them with VICM minus VID over 2 for VI1 and VICM plus VID over 2 for VI2. And then I will collect all the terms that multiply VID and all the terms that multiply VICM. And now I get a nice expression. This is AD times VID plus ACM times VICM. My goal is to build a difference amplifier. I only want VO to be AD VID. I want ACM VICM to disappear. So how can I make it disappear? Can I make ACM 0? Well, possibly. Let's look at the ACM expression. That's ACM. It's R1 times R4 minus R2 times R3 over R1 into R3 plus R4. And actually, it's quite easy to make it 0. If I make R1, R4 minus R2, R3 0, in other words, if I make R1 over R2 equal to R3 over R4, this will make this disappear. This becomes 0. And this becomes 0. So if we make R1 over R2 equal to R3 over R4, the output will only be AD times VID. And this is what I want. I want an output which is just some gain times the difference. And the condition is quite easy to achieve. I mean, just make R1 over R2 equals R3 over R4. What kind of gain do we get? What would be AD in this case? It will be R2 over R1. So if you want a certain gain, say 10, make R2 10 times R1. So this will give you the gain. And to make ACM 0, make sure that R3 over R4 is 1 over 10. So R3 over R4 equals 1 over 10. And R1 over R2 equals 1 over 10. We'll make ACM 0. And we'll make AD 10. We'll give you the gain that you want. And the output will only be this gain times the difference between the two inputs. So you will only amplify the difference. If the two inputs are equal, there's no output. If there's any difference between them, this difference is multiplied by 10, and the output will be that.